So today we have an interesting geometrical problem. We take a rectangle. Now we take the length and breadth of this rectangle as variables a and b respectively. Now taking the base of this rectangle as the diameter, we draw a semicircle inside it. Now we draw a line segment BM such that it is tangent to the semicircle that we have just drawn and the point M lies on the left side of the rectangle. Now we inscribe two congruent circles inside the diagram. This particular circle over here is tangent to both sides of the rectangle and it is also tangent to the line segment BM. And talking about this one, so this is tangent to the side of the rectangle, to the line segment BM and also to the semicircle. Now this kind of arrangement of the semicircles, the tangent line and the congruent circles can be only possible in some special types of rectangle. Now the thing that makes a rectangle special is the relation between its length and breadth. So ultimately the question over here is to find the relation between the length and breadth of the rectangles in which this kind of arrangement is possible. To be more precise, you have to find the value of the fraction a upon b. So this is Anmol and now let us see the solution. How can we solve this problem? Okay, now let us start with the solution part of the video. So the first thing that I will do is I will take the radius of the circles as a variable x. Note this thing that both of the circles are congruent, hence both of them will have the same radius. Now basically the solution of this problem is in two parts. In the first part of the solution, the main focus would be on this particular circle, and in the second part, the main focus would be on the second circle. And from both of the parts, we will get two equations and combining them at the end will give us the final answer that we are looking, that is the value of the fraction a upon b. Now as I told you, let us start with the first part of the solution in which the major role would be of this particular circle. But before that, let us find out the radius of the semicircle. So for that, let us mark the center of the semicircle as a point O. Now it is already given that the diameter of the semicircle is the length of this rectangle. Length of the rectangle is having a value a. Therefore the diameter of the semicircle is having a length a. Hence the radius would have a value a upon 2. Okay. Now let us talk about this particular circle. So let me just zoom over there. So now we can clearly see that this particular circle is tangent with the lines over here and with the semicircle over here. So if I basically draw the radius to these 2 points, the angle over there would be 90 degree because of the theorem. The angle formed at the intersection of a tangent line and the radius is always 90 degree. Now what about this thing, that is a circle tangent to another circle? So there's a nice theorem related to this also. If there are two circles that are tangent to each other either externally or either internally, in both the cases, the center of both of these circles and the tangent point would always be collinear. Either the case is external or either the case is internal. Okay. So the same thing can be utilized over here. As we can see, we have a semicircle tangent to a circle. So if I draw a line segment from the center of this semicircle to the center of the circle, it will also pass through this tangent point and this line would be a straight line. And simply that means the center of both of the circles and this tangent point would be collinear. Now we can see that the distance from the point O to this tangent point is the radius of the semicircle, hence it would have a length a upon 2. The distance from the tangent point to the center of this circle is the radius of that circle and we have already taken it as a variable x. Therefore, the complete distance from the point O to the center of this circle would be simply a upon 2 plus x. So let me write down that thing over here. So the complete length over here is ultimately going to be a upon 2 plus x. Okay. Now what I will do is I will simply take the center of this circle and drop a perpendicular from this point to the base of this rectangle. Now the thing to be noted over here is that the angle C is 90 degree because it is the corner of the rectangle. Hence in this particular quadrilateral, all the 4 angles become 90 degree. In a quadrilateral, all the 4 angles are 90 degree, hence it is a rectangle. In rectangle, opposite sides are equal. Now look carefully, this particular distance over here is the radius of the circle, hence it would have a value x. And as I have told you, this quadrilateral is a rectangle. This length would be equals to this length. So ultimately the length from here to here would be equals to x. The complete length from O to C was a upon 2. The distance between these perpendiculars we have got as x. Therefore the remaining distance, that is going to be from the point O to this perpendicular that we have dropped would be equals to a upon 2 minus x, that is longer minus the shorter. Now look carefully, here we have a right angle triangle. The hypotenuse is a upon 2 plus x, the base is a upon 2 minus x. Hence, by applying the Pythagoras theorem in this right angle triangle, the value of the height will turn out to be square root of 2ax. Now recall that we have got this quadrilateral as a rectangle. In rectangle, opposite sides are equal. Therefore, this length would be equals to this length. So let me just remove this b from here. So the distance from this perpendicular to this point C is going to be square root of 2ax. The complete length from B to C is the breadth of this rectangle that was given as a variable b. Therefore, the remaining distance, that is from the point B to this perpendicular, would be simply longer minus the shorter. So that would simply give me b minus square root of 2ax. Now this was some basic markings of the lengths present in this diagram. Now we are going to proceed to an important step. So as I have told you in many of my videos that if we have two lines like this, and we have two circles that are tangent to both of these lines, either they are touching to each other or not, that thing is not mattered over here. If there are two circles that are just tangent to both of these lines, if they touch, well and good, and if they don't, there is no need only. The important thing over here is that we can draw a straight line from the corner that is passing through the center of both of these circles, and also this line bisects this angle equally. So the proof of this thing is also very easy. First of all, take the case of the smaller circle. As it is tangent to both of these lines, I will draw the radius, and it would be simply perpendiculars at the tangent point. Now we can clearly see that this right angle triangle above and this right angle triangle below are congruent to each other because of right angle hypotenuse side. Hence, this angle and this angle would be equal. So if I just take this complete angle as a, both of these combined together gives us a. Therefore, the value of each angle would be simply a upon 2. Now let us take the case of this bigger circle. So I can again see that the circle is tangent to both of these lines. I will draw the radius to that points. The angle formed over there would be 90 degree. I will draw a line segment from the point A to the center of the circle. This right angle triangle congruent to each other because of right angle hypotenuse side. Hence, these two angles in these two triangles become equal. Two equal angles combined give me the complete angle A. Therefore, the value of each of this angle would be a upon 2. So what I can see is that if I draw a line segment from the point A to the center of this circle, it bisects the angle A equally. And again, if I draw a line segment from the point A to the center of the bigger circle, it again bisects the angle A equally. This means both of these lines are going to coincide each other. That means if I draw a line segment from the point A to the center of the bigger circle, it also passes to the center of the smaller circle. So now the same theorem I am going to utilize in this question. So we can see that we have two line segments. The first line segment is BM. Let me change the color. Let us again take yellow. So we have the line segment BM, and the other line segment we have is BC. So we can see that the blue circle is tangent to both of these lines. Okay. The semicircle is also tangent to both of these lines, one over here and one over here directly. So we can see that all the conditions are fulfilled for the theorem that we just saw. So we can just draw a line segment from the point O to B, and this will pass through this tangent point also and the center of this circle also. Okay, so this was an important step in the first part of the solution. Now look carefully, we can see that from the line segment BC we have this perpendicular and this perpendicular. So we know this thing very well that from a straight line, if we have two perpendiculars, both of them are going to be parallel to each other. So we can use the same thing over here. Hence this line and this line would be parallel to each other. Therefore, the corresponding angle become equal. So if the value of this particular angle has been taken as theta, this angle over there would again be theta. Now we can see that the smaller right angle triangle and this right angle triangle are going to be similar to each other because two of the angles in both of this triangle are equal to each other. Hence two triangles become similar to each other by the property of angle. So if you write down that thing, and according to the correspondence, if you take the ratio of the sides, it will turn out to be like this way. Height of this right angle triangle upon the height of this right angle triangle equals to base of this right angle triangle upon the base of this right angle triangle. So let us note down that thing. So b minus square root of 2ax, that is the height of the upper right angle triangle, upon the height of the bottom one, that is square root of 2ax. This thing would be equals to the ratio of their bases. So the base of this upper right angle triangle is ultimately the radius of the blue circle that has a value x, divided by the base of the bottom right angle triangle, that is a upon 2 minus x. Simplifying this whole fraction would simply turn out to be a minus 2 times x, and the 2 in the denominator will go in the numerator. Okay. Now let us do the cross multiplication to simplify this thing. So I will get ab minus 2bx minus a times the square root of 2ax, negative negative positive, 2 times x the square root. This thing equals to 2 times x the square root, and this both will get cancelled out. So finally we will have the equation like this way: a minus 2bx equals to a times the square root of 2ax, and this is the first important equation, and here ends the first part of the solution. Now we are going to proceed to the second part of the solution, in which we are going to deal with the second circle that is present on the top left corner. So I'm just going to remove all these things that we have done for this one. Now the first thing I will do is I will take this circle over here, and note this thing that this circle is tangent at this and these 3 points. Hence if I'll draw the radius to these 3 tangent points, the angle over there would be 90 degree. The theorem I have told you before, the angle formed at the point of intersection of a tangent line and the radius is always 90 degree. Okay. Now look carefully that the angle A is also 90 degree because it is the corner of the square. This particular quadrilateral over here, all the 4 angles become 90 degree. This length equals to the radius of the circle, that is having a value x. Hence this complete quadrilateral becomes a square with all the sides having a value x. So the length from A to this perpendicular become x. Okay. Now what I can see is that I simply draw a line segment from the center of the circle to the point B. This right angle triangle and this right angle triangle become congruent to each other because of right angle common hypotenuse, and these two sides equal because they are the radius of the same circle. So once two triangles are congruent, rest of the things between them become equal. So the length from the point B to this perpendicular would be same as the length from the point B to this perpendicular. Now what can you say about this length? So look carefully, as we have got that this is a square. So the length from A to this perpendicular would have a value x. The length from A to B is the length of this rectangle having a value a. Therefore the remaining length, that is from this perpendicular to the point B, would be simply longer minus the shorter, and that would give me a minus x. And as I have told you, that length is ultimately equals to the length from the point B to this perpendicular, and that would again be a minus x. Okay. So no need of this above one and also this one. Okay. The thing we just did by using the congruent triangles and all this thing, that is also okay, and you can directly use the theorem, that is, if we draw two tangent lines from the same point to a circle, both of them will have the same length. So now let us utilize that theorem for the semicircle. We can see that from the point B we have this two tangent line drawn, hence both of them will have the same length. The length from B to C is the breadth of this rectangle having a length b. Therefore the length from B to this tangent point would also have the same length, that is b. Now I can see that the length from B to this first tangent point is b. The length from B to this second tangent point, that is with the circle, is a minus x. Therefore the length between these two tangent points would ultimately be longer minus the shorter, and that would give me a minus x minus b. So let me just draw the radius for this tangent point in the semicircle, and as we have just seen, the distance between these two would be a minus x minus b. The length from here to here is the radius of this blue circle having a length x. The length from A to D is the breadth of this rectangle having a value b. This much length is equals to x. Therefore the remaining distance, that is from this perpendicular to this point D, would be longer minus the shorter, and that is going to be b minus x. Okay. Now what I will do is I will simply drop a perpendicular from the center of the blue circle to the base of this rectangle. So now we can see that this angle is 90 degree because it is the corner of the square. This quadrilateral becomes a rectangle, the same thing that we did over there. So now we can see that this distance is x. Therefore this distance is equals to x. The complete distance is a upon 2. Therefore the remaining distance, that is the distance from the perpendicular to the point O, would turn out to be a upon 2 minus x. And also this length would be equals to this length. This length we have got as b minus x. Therefore this perpendicular would also have a length b minus x. Now what I will do is I will simply draw a line segment joining the center of this blue circle and the center of the semicircle. Now look carefully for this green line. It is the hypotenuse for this right angle triangle. So let me just draw this right angle triangle outside. So this is the height, so the height is like this way, this is the base, and we have the hypotenuse like this way. The length of the hypotenuse we don't know, so let it be equals to y. The height of this right angle triangle we have got, and that is b minus x. The base of this right angle triangle we have got, and that is a upon 2 minus x. And now I will take a beautiful arrangement from this diagram. So the arrangement is like this way. So let me just take this thing away from this diagram. That is very simple. Now let me just draw the arrangement. So the arrangement I am talking about is like this way. We have 3 line segments arranged like this, this and this, and then we have this green line that we have drawn joining the centers. From this point to this particular point, these angles are 90 degrees. You can look carefully. I am talking about this particular pattern. This distance is radius of the blue circle having a length x. This distance is the radius of the semicircle having a length a upon 2, and this distance we have got as a minus x minus b. You can look carefully. This thing I have just drawn outside. Now this thing can be utilized very nicely. I will simply extend this line and I will drop a perpendicular from here to here. So we can see here we have formed a rectangle, hence opposite sides would have the same length. This distance is a minus x minus b, therefore this length would be a minus x minus b. The length of this rectangle is a upon 2, therefore this side also a upon 2. Now the complete length from here to here would be a upon 2 plus x. So let me write that thing over here. So the length would now turn out to be a upon 2 plus x, that is ultimately the height of this biggest right angle triangle. Now what I will do is I will simply remove this thing from here and also all these things, and I will just keep this line as a straight line. The length from that point to over here was something like x, and the complete distance we have already got as a upon 2 plus x. Okay, now I can see that here we again have a right angle triangle, and the hypotenuse of this right angle triangle is again the green line that we have just taken as a value y. So if I apply the Pythagoras theorem in this right angle triangle, I will get b minus x the complete square plus a upon 2 minus x the complete square equals to y square. And by applying the Pythagoras theorem in this right angle triangle, I will get a upon 2 plus x the complete square plus a minus x minus b the complete square equals to y square. Hence, by comparing this equation, we can say that b minus x the complete square plus a upon 2 minus x the complete square would be equals to a upon 2 plus x the complete square plus a minus x minus b the complete square. Now the task over here is to simplify this equation. So the opening of this thing will give me b square plus x square minus 2bx plus the opening of this thing will give me a square upon 4 plus x square minus ax equals to opening of this thing will give me a square upon 4 plus x square plus ax, and the opening of this thing will give me plus a square plus x square plus b square minus 2ax plus 2bx minus 2ab. Now we can see that some common terms are present on both sides of the equals to sign, hence they can be eliminated. So the first thing I can notice is a square upon 4. Now I can see positive b square, then we have positive x square, again a positive x square, again a positive x square. Here I can see plus ax minus 2ax, that will give me negative ax, and that can be factored out with this particular one. So what is finally remaining is negative 2bx equals to this a square, this positive 2bx, and this negative 2ab. Simplifying this thing will give me the value of 4bx equals to 2ab minus a square. And here comes the end of the second part of the solution, and this is the second important equation. Recall the first important equation. This was the first important equation, and now we have the second important equation. Now let us combine this thing. So the first thing that I will do is I will replace the value of negative 2bx in the first equation with the help of the second one. As we can see, in the second equation we have the value of 4bx. So if I divide this equation on both of the side by 2, I will get the value of 2bx equals to ab minus a square upon 2. So now we ultimately have the value of 2bx, so this can be replaced in this first equation. So ab minus 2bx, instead of that the value that we have just got, and that is ab minus a square upon 2, this thing equals to a times the square root of 2ax. Now opening this bracket over here, therefore negative of positive ab would be negative ab, negative of negative a square upon 2 would become positive a square upon 2. This and this got cancelled out, so I will have a square upon 2 equals to a times the square root of 2ax. This a will factor out this thing, and now if I just do the cross multiplication and square both of this side, I will get a square equals to 4 times 2ax. So now what I will do is I will take the second equation again, and this time I will divide the whole equation by 4 times b. So I will get the value of x equals to 2ab minus a square upon 4 times b. Now this value of x I will put over there. So I will get a square equals to 4 times 2 times a multiplied with 2ab minus a square upon 4 times b. Now let us simplify this thing, so I can first of all see that 4 and 4 got cancelled out. This a will make this a square a simple a. This b can be just multiplied on the other side, so I will get ab equals to, this 2 can be opened up with this bracket, so 4ab minus 2a square. Doing some adjustment will give me 2a square equals to 3ab. This a will make this a square a single times a, and dividing both of these sides by 2 times b will give me final value of a upon b equals to 3 upon 2, and this is the answer that we were looking for. So this was my way to solve this particular problem. If you have any other method other than this, or else if you have any other question that you think I should try, you can do comment below. And if you want to share some kind of picture of the solution or question, you can email me, or else you can send it to me on my Instagram. The link is in the description.